here. Right, pause. Okay, it's already recording. All right, okay, so kita put kat sini. Okay, all right. So in our previous lecture, which was not yesterday, which was last week, we have talked about so far until activation energy. Okay, the collision theory, and then activation energy, where you learn about the effective collision. Okay, so there are two rules, there are two factors that you should know for an effective collision to take place, which the first one will be the proper orientation, and then secondly, in terms of the energy, okay, the minimum energy required to overcome the activation energy. Okay, and you also have learned on how to draw a profile energy diagram, okay, energy profile diagram for an endothermic and exothermic reaction, and how you should represent the EE, okay, the activation energy. So the last checkpoint that we did is checkpoint 11, okay, this one. So we have discussed this one already, and we have one more checkpoint that we haven't discussed, which is checkpoint 12. Okay, all right, so let's go through very quickly on the question. Question 1. According to the collision theory, choose one of the following statements which best describes the conditions needed for a successful formation of a product. So as you can see, we have the answer already at the bottom there. Okay, the answer is C, but let's just go through each one of them. Okay, and let's check what is missing for A and B, and why these two options are not considered as the best, okay, description to represent a successful formation of a product. Okay, all right, so A. Okay, which best describe the condition needed for a successful formation of a product. So A, the collision must involve a sufficient amount of energy provided from the motion of the particle to overcome the activation energy. So this statement is correct, okay, but it's not complete. Okay, all right. In order to have a successful formation of a product, ataupun having said that, it also means an effective collision. Okay, it also means effective collision. So for an effective collision to take place, yes, okay, the collision need to have sufficient energy. That sufficient energy is used to overcome the EA. And one more thing, okay, the orientation need to be properly oriented. Okay, if dia ada the energy, sufficient energy, but the orientation is not correct, the product cannot be formed. Okay, the product cannot be formed. So A is not the best description, but it's not wrong. It's just that dia tak complete. It's not complete. Okay, right. B. How about B? What's the problem with B? The relative orientation of the particle has little or no effect on the formation of the product. Okay, so this is entirely, the whole statement is wrong. Okay, orientation plays a very vital role, especially when forming the product. So this is B is wrong. Okay, right. C, the energy of the incoming particle must be above a certain minimum value. This is in terms of the energy, and the relative orientation of the particle must allow for formation of new bond in the product. Okay, so in C, we have in terms of energy, okay, the energy must be sufficient. And then secondly, it also mentioned in terms of orientation. So that is why C is the best description ataupun the best describe for successful formation of a product. Okay, right. So moving on. Okay, effect of concentration or reaction rate. Okay, all right. So earlier on, we have learned about the factors that can affect the reaction rate. Okay, where we have concentration, then we have temperature, then we have um, surface area, the nature of the reactant itself. Okay, and then what else? The catalyst. Okay, the presence of catalyst. Okay, so now we're going to look at the effect of concentration on reaction rate. So the easiest way to uh, to increase the rate of reaction is by increasing the concentration of the reactant. So by increasing the concentration of reactant, what we are trying to do is to increase the number of molecule colliding. Okay, number of molecule colliding. So when we increase the concentration, the number of molecule will also increase, and with that, the number of collision will also increasing. And therefore, the probability of an effective collision will also increase. Finally, the rate of reaction. Okay, the rate of reaction will also increase. Okay, all right. So concentration can influence the number of effective collision per seconds. Okay, all right. So this is with subject with time. So it can increase the rate of reaction actually. Okay, because it increases the number of effective collision. Therefore, it also helps in increasing the effective collision per second. Okay, all right. So an increase in the concentration of reactants leads to a larger number of collision, increase the frequency of effective collisions, hence increasing the rate of reaction, like I said just now. Okay, like I said just now, the increase in concentration actually increase the number of particles in the reaction, and therefore it also increase the number of collision. Bila number of collision increases, of course, the frequency of effective collision, okay, maksudnya pertambahan probability of effective collision to take place is also increased, and this will increase the rate of reaction. Okay, right. The number of collision depends on multiplication between numbers of reactant particles exist, not on their sum. For example, concentrations are multiplied in the rate law, not added. Okay, all right. So this again, I would like to remind you, if we can predict the number of collision that take place, kita boleh predict. Okay, we can expect the number of collision that will take place by multiplying the concentration. Okay, I mean by multiplying the numbers of reactant particles. Kita multiplykan dia, bukan kita tambahkan dia. Okay, the easiest way will be kita multiply the number of particles of reactant present in the reaction. Okay, the reason we say so is because in the rate law, okay, remember in the rate law, rate is equal to K times concentration of reactant A, katalah A raised to a power, raised to its power, and then multiply with B raised also to its power, kan? Alright, as you can see, so the concentration of A and the concentration of B, so we have an operation involved there, which is a multiplication reaction. Okay, bukan tambah kan? Dia bukan tambah, dia darab dekat situ. Dalam rate law tu, concentration side by side, which represent the multiplication operation. Okay, so based on that, kita come up with this conclusion that the number of collision is based on the reactant, the multiplication between the number of reactant, not on their sum. Okay, all right. So let's look at an example here. So A plus B. Okay, so this is reaction A plus B producing AB. So we can predict the number of possible collision. Okay, the number of possible collision is the product, okay, which is not the sum of reactant concentration. Okay, all right. So the number of possible collision also represent the product form later on. Okay, all right. So we can predict the number of collision by multiplying the number of particle that we have for reactants. For example, we have 2A kan? We have 2A and 2B. So 2 times 2 will be 4. Therefore, we have 4 collision. Kebetulan pula 2 tambah 2 is also 4. Okay, itu hanya kebetulan sajalah. But kita consider for the multiplication. Or you can also consider in terms of the probability of collision. Okay, alright. A1 probability of first probability will be A1 will collide with B1. And then A1 can also collide with B2. So that is already two what do you call it? Two possibility. And then A2, A can collide with B1 and then it can also collide with B2. So 2 plus 2, okay, is equal to 4. So satu ni boleh collide 2 kali. So this one also can collide with 2 times. So 2 times 2 is equal to 4. Okay, alright. What happen if we add another A? If we add another A, the easiest would be kita kalau multiply je terus 3 darab 2, kita dapat 6 collision. Okay, kita bukan 3 tambah 2. No, we don't do that. We multiply the particles. 3 times 2 will be 6 collision. Okay, kalau you nak buat total, in terms of total, you kena kira lah A1 possible untuk langgar dengan B1. A1 can also possible to langgar with B2. To produce product, we are talking about product, bukan A langgar dengan A. A dengan langgar dengan A will not produce product. A must collide with B to produce AB. Okay, alright. Another probability will be A2 collide with B1, A2 collide with B2. So this 2, and then this is also 2. So 2 plus 2 plus 2 will be 6. Kalau you nak pakai tambah pun, that is the style. Bukan 3 tambah dengan 2. That is wrong. Kalau you nak pakai style tambah, you have to consider for the probability. So 2 plus 2 plus 2. Then only you get 6. Okay, alright. So if we add another B, okay, what happened to the number of collisions? So of course, it will increase the number of collisions. So we can predict the number of collision as 9 collision because we have 3 times 3 is equal to 9. Okay, alright. Okay, so that is for concentration, the effect of concentration on reaction rate. Okay, alright, so the second most important factor that can affect the reaction rate is temperature. Okay, so for most reaction, endothermic or exothermic, the rate of reaction increase exponentially, okay, with increasing temperature. Okay, when the temperature increases, the rate of reaction will also increase. Okay, according to the kinetic molecular theory of gases, okay, remember this KMT, we have learned this in topic 4 during our semester 1, okay, state of matter, remember gas law last time. So we have four description of KMT. So what are those? Remember, ring a bell tak? So benda yang sama, kinetic molecular theory of gases. Apa yang kita predict for the gases to apply the kinetic molecular theories of gases. Okay, kita assume dia tidak ada volume, remember, because they are far apart with one another and they don't have the interparticles attraction, remember? Those are the KMT lah. Okay, the content of KMT. So according to the KMT theory of gases, increasing the temperature increases the molecular speed. Okay, this is so because I've mentioned to you before, okay, when temperature is increased, what happens is that we heat lah. Basically, how do we increase the temperature, guys? By heating the reaction. Okay, by heating the reaction. So when we increase the temperature, we heat the reaction. So what happens is that we are actually supplying supplying extra energy to the reaction, to the particles. So the particles absorb. Okay, the particle absorb the energy and now having extra energy. So it causes the speed, okay, the speed of the molecule, okay, to become faster. Because they have extra energy now. So they move faster, they collide more, okay, so they become hyper kan. So that's why temperature is directly related to kinetic energy. Okay, and this kinetic energy is also directly related to molecular speeds. When kinetic energy increases, okay, when kinetic energy increases, the speed, the molecular speed, the particle speed also increase. Okay, all right. As molecules move faster, they collide more forcefully with more energy and more frequently, and this increases the reaction rate. The temperature is directly proportional to average kinetic energy of the molecule. Temperature is directly proportional to average kinetic energy of the molecules. Okay? Alright, so molecules are moving at different speeds at any given time. Okay, even though the molecules are all the same type, contohnya we have nitrogen kan, we have molecules of nitrogen. Okay, so not all nitrogen molecule, not all of them having the same speed. Dia tidak bergerak pada speed yang sama, even though they have the same molecular weight, okay, but they do not move. They do not necessarily, tidak semestinya they move at the same speed. Okay, so how do we represent? They are actually, dia adalah nitrogen, okay, molecule nitrogen, cuma dia punya speed dia tak sama. Okay, how do we, represent the whole collective nitrogen molecule? Okay, so that is why we use average speed. Okay, we use average speed to represent the whole collective with respect to the gas lah. Kalau respect yang saya cakap tadi, respect to nitrogen gas. Dia macam ni, kalau you adalah S13 kan, in S13 kita nak find out apa hobi S13, student S13. Okay, banyak tak yang suka berlari? Sebab we are talking about speed kan, so saya teringat lari je lah. Okay, banyak tak yang suka berlari? Not all of you prefers running kan. So ada yang suka berjalan, ada yang suka tidur, ada yang suka berlari kan. Kita kalau nak check each one of you, okay, kalau kita check kan berbeza-beza dia punya preference. Okay, alright, tapi kita ambil lah secara kolektif. Kolektif as in average. Okay, alright, turn out rupanya hampir 80% suka berlari. So kita just pakai average macam tu to represent a data. So daripada kita kena sebut 25 student tu, okay, student pertama suka berlari, student kedua suka berjalan, student ketiga suka tidur, student keempat suka berlari, student kelima suka berlari. Penatnya nak sebut. Okay, so that's why we have average to describe the collective of molecules. Okay, ataupun a collective of class, group, macam S13 just now. Okay, alright, so to represent the relationship between speeds and temperature, okay, this is also, we have learned this one during our semester 1, again in the same topic, which was state of matter, okay, dalam gas tu, Maxwell-Boltzmann distribution, okay, that shows how the speed energy of moving particle in a mixture change with temperature. Speeds dengan temperature. Okay, they relate speeds and temperature, and also speeds normally in terms of, we can represent the speed in terms of energy as well. Okay, sometimes we can use speed, sometimes we can use kinetic energy. So it's actually carries the same meaning, because we know that speed is directly proportional to kinetic energy. Okay, right. So molecules are moving at different speed at any given time, as shown by the Maxwell-Boltzmann distribution curve below. Okay, the area under distribution curve is proportional to the total number of molecules. Okay, all right. So you should know how to represent the Maxwell-Boltzmann curve well. Okay, so what should be present? What should be in your Maxwell-Boltzmann distribution curve? Okay, all right. So of course you have to have axis. Okay, axis for y and also x. So this one will be fraction of molecules, ataupun sometimes we can also use number of molecules. Okay, for the y-axis, number of molecules. And here, kalau dalam state of matter last time, kita pakai speed, remember? Molecular speed kan? It's actually boleh. We can use kinetic energy to represent the molecular speed. Okay, alright. Okay, so this is how the curve look like. Okay, dia macam dia starting here. Okay, alright. Remember, kalau Maxwell-Boltzmann distribution curve, dia based on the area below the curve, the area under the graph. Okay, so fraction of maksudnya area bawah graph ni represent number of molecules. So as you can see dekat kawasan sini kan around this area sebelum hijau ni. This one here until here. Okay, so this is where the kinetic energy is at the lowest. Okay, kita bagi kepada 3 lah. Kita ada 1. Yang ni lagi 1, number 2 and this one, the third one. So this is the closest to 0, betul tak? So bila dia closest to the 0, maksudnya kinetic energy is at the lowest. Okay, around here. So at the lowest. So as you can see, luas bawah graph for this part here pun tak berapa well representing the ni, tapi adalah the idea is there. Okay, right. Kita akan tengok later from textbooks contoh. Okay, so just nak highlightkan kat sini a few molecules having low energy. Okay, having low energy. Maksudnya sikitlah kita ada fraction of molecule having lower energy. And then kat kawasan tengah ni, nampak tak? Dia punya kawasan this one, hijau, kawasan nombor 2, this is number 1, this is number 2. Kawasan hijau, okay, dia paling tinggi. Luas bawah graf dia yang paling besar. Kalau kita nak compare tu 1 dengan nombor 3. Okay, alright. So this is where most of molecule having values the speed ataupun kinetic energy somewhere in the middle. This usually represent the average. Kan, sebab dia paling banyak. So normally the average would be somewhere in the middle, yang tengah ni. Sebab dia paling tinggi here, nampak? Graf bawah, the luas bawah graf would be, the highest here. Okay, alright, ini in the middle. So we also have the kawasan nombor 3 ni. Ini tengah-tengah kan, kinetic energy. And this one sampai hujung ni is the kinetic energy at the among the highest lah, among the highest. Here will be the highest, but this one is among the highest. Okay, so tapi kat sini dia tak banyak kan, see, nampak a few molecules have high energy because the area below the graph is not that much compared to the one in the middle, the area in the middle, yang green colour ni. Okay, right, remember luas bawah graph. Okay, it is proportional, okay, they're based on area and the distribution curve is proportional to the total number of the molecules. Okay, alright, so this is the one that we used to have last time, okay, to compare at different temperature. Okay, alright, so let's look at the figure. Figure below shows how the speeds ataupun in terms of energy of moving particle in a mixture change with temperature. So as you can see, we have T1 which is at the lower temperature and also T2 at the higher temperature. Okay, kita nak compare. Okay, the area under each curve is the same. So total number of molecules used for T1 and T2 are the same. Okay, alright, so both curve actually have the same area, below the curve. Okay, it's just that yang warna biru ni dia menegak sikit, yang the red one is flattened to the right, dia melandai sikit. But the area below the graph is actually the same untuk dua-dua graph. Okay, yelah, you nak compare in terms of temperature. So the rest all should be kept constant. You tak boleh lah nak compare a different temperature, tapi this one number of molecule dia sikit, yang T2 ni number of molecule dia banyak. Of course the average speed will be different, right? Kan? So tak boleh macam tu. So when you want to study the temperature, when you want to study the effect of temperature, only the temperature should be varies ataupun should be changed. The rest should be kept constant. Barulah kita boleh compare apple to apple. Faham? Barulah fair dia punya comparison. So that's why saya kata the area below the graph for blue curve and the red curve, the area are the same. Cuma bentuk dia saja. Yang ni tinggi sikit, yang red one tu dia melandai, flatten to the right. Okay, alright. So what can we conclude from this figure? Okay, so as you can see, kita akan compare the area below the graph. Okay, alright. So this dashes line, what does this represent? This dashes line represent the EA, guys, the minimum energy required for the reaction, which is the EA. Okay, so as you can see, for T2, okay, at higher temperature, reaction conducted at higher temperature, the area below the graph, which is red campur dengan biru ni, red campur dengan biru, the area below the graph is larger. Okay, the area below red graph. Red curve is larger than the area below blue. Okay, nampak tak? Compared to biru, dia punya area dia kawasannya biru ni saja. So maksudnya apa? At higher temperature, more molecules have extra energy to overcome the activation energy. Okay, so you must be able to translate. Okay, you know that the area is larger. So what is the explanation behind it? Okay, so it shows that at higher temperature, the particle have extra energy. Okay, more particles, sebab more particles represent the area below the graph. More particles have extra energy to overcome the EA. Okay, right. So the shaded area show molecule having energy equal to or greater than EA at T1 and T2. At T2, larger fraction of molecule has higher kinetic energy. Okay, at T2, the red graph lah, the red curve. So larger fraction, more molecule has higher kinetic energy, and therefore they can overcome the T. Okay, alright. So as temperature increases, the rate of reaction increases. So that's the relationship that we learned so far. Okay, alright. Temperature increases, the rate of reaction increases. Okay, due to what? This is the reason why. Because more fraction, more molecule can overcome the EA. Okay, alright. This is also the same thing. Okay, it's just that maybe it is more clearer. Okay, because so T1 is lower than T2. The temperature is lower than T2. But look at the shaded area under the curve. Okay, so the size of the shaded area under the curve for T2 is larger. Nampak tak? Lagi besar. Dia sebenarnya cover sampai sini. Okay, the shaded are proportional to the total fraction of collision that involve the minimum activation energy. So more molecule can overcome this EA. This is the EA. Nampak tak? Lebih banyak molecule can overcome the EA. Okay, when the reaction is conducted at higher temperature. Okay, all right. The fraction of the molecule able to react has almost doubled by increasing the temperature by 10 degrees Celsius. That causes the rate of reaction to almost double. Okay, so just by increasing the temperature to 10 degrees Celsius, dia punya different dia tu 10 degrees Celsius, the rate of reaction also almost double. Okay, katakanlah 10 to 20. Okay, so this is the difference between these two temperature will be 10 degrees Celsius kan? 10 degrees Celsius is different, but the rate will increase double. Okay, ni kita doublekan lah, 10 to 20 kan double kan? So the rate will also double. Okay, alright. So now, yeah, so far we have the relationship between temperature and reaction rate. Temperature and reaction rate. So we know that when temperature increases, the rate increases. Betul tak? Temperature increases, rate increases. But now, how do we relate the rate and the rate constant? What is the relationship between rate and rate constant? What is the relationship between temperature, rate, and rate constant, guys? And rate constant. Okay, alright. So kita boleh dapat the idea. We can get the idea from the rate law. Okay, we know that rate law. Okay, so this is the relationship that we have so far. Rate is directly proportional to T. So when T increases, rate also increases. And we know that rate is also directly proportional to K. So how do we know that rate is directly proportional to K? Based on rate law lah. Okay, rate law. Okay, for example, kata rate law is equal to K times A, katalah simple reaction, A to raise to a power of 1. Okay, alright. So as you can see, when a rate increases, K also increases. Ataupun K increases, rate also increases. So this is directly proportional. Okay, alright. So we can relate that when T increases, it will also increase the rate constant value. Okay, it will also increase the rate constant value. So that's the relationship that we can get from temperature and also rate constant. Okay, look at the data that we have given here. These are the rate constant K temperature for the hydrolysis of an ester. So hydrolysis of an ester is the reaction. Okay, so this is the data provided to us. Okay, we have 4 experiment of the same reaction, but we varies the temperature. As you can see, nampak tak concentration of the ester, and these two are the reactant. These two, ester and H2O, are the reactant used in this reaction. You nampak tak the concentration remain the same. Okay, we do not vary the concentration because we don't want to study the effect of concentration. Kita tak nak study. We don't want to study the effect of concentration, but what we want is to study the effect of temperature on the rate and also on the rate constant. See, nampak tak? Okay, experiment 1 is conducted at 288. Experiment 2 at 298, experiment 3, 308, experiment 4, 318. And then we measure the rate. So as you can see, the rate increases because as the temperature increases, this is our expectation, this is our prediction, right? And then we prove it, okay, by doing the experiment. It is confirmed that When the temperature increases, the rate also increases. And what happened to the K, guys? Okay, what happened to the K? The K also increases. Okay, the K also increases. Okay, so please jot down somewhere. Dekat sini saya nak cakap. Okay, please make sure that you jot down this information. Saja je saya tak nak tulis. So that you jot down. Extract the information from what I'm about to explain to you guys. Okay. The only factor, okay, the only factor that can affect the rate constant would be the temperature. Okay, ataupun saya rearrange balik. Temperature is the only factor that can affect the reaction rate, the rate of reaction. Okay, so concentration, catalyst, surface area, the nature of the reactant, these four, okay, these four are these four cannot, okay, change the rate constant, the value of rate constant. Okay, yes, they can affect the rate, but not the rate constant. Again, the only factor that can affect the rate constant, that means the value of rate constant will be changed, okay, will be changed if we varies the temperature, if we change the temperature. Okay, all right, faham ya? All right, so that's why concentration, when we calculate when we determine the effect of concentration last time, okay, the value of K remain constant. Apa tak yang kita pakai the initial rate method last time? Okay, what happened to the K when we try to calculate the K? The K will remain constant, right? Same goes to other factors like catalyst, surface area, and whatnot. So those can only affect rate, but not rate constant. Okay, right. Okay, if we were to represent this rate constant versus temperature, okay, rate constant versus temperature, so we get a curve, okay, we get a curve, and this is a positive curve because when you try to find the slope, okay, you will get a positive value. Okay, you will get a positive value. So the rate constant K increases exponentially with T. Okay, with